Good afternoon, everyone. Thank you for joining us for this webinar featuring Allonnia, a MICA member here with us. We're very excited to have them to present on their process that they've been working very, very hard on developing. That solved a number of problems in them. Oh my goodness, everyone's just coming in and I'm getting pinged and pinged and pinged. Any case, I'm very excited to have Allonnia here. My name is Kyle McCall. I am the Director of Commercialization Services and Member Relations with the Mining Innovation Commercialization Accelerator, which is a program run by the Center for Excellence in Mining Innovation. MICA is a national network of innovation in mining, for mining. We're designed to bridge the gap between innovation and commercialization and support companies as they cross that chasm and try and get their technologies adopted by the mining industry. And we do that by working with regional partners from coast to coast. We had a funding program, and then we've got other supports that we offer, other supports and services that we offer to our members. One of which is webinars just like this. So again, very excited to have Allonnia with us today to talk a little bit about their company and their solution. With us, we have Dan Stigers, their VP Business Development, and Karrie Radloff, who is one of their mining engineers, mining and process engineers. So with that, I will turn it over to Dan to introduce Allonnia, and I'm going to turn my camera off and shut up. Thanks, Dan. All yours.
Thanks, Kyle. And thanks, everyone, for joining. Looking forward to this presentation. So today we're going to talk about selective gangue removal and what that means essentially for the mining industry. And it should come as no surprise to this group that there's a rather large supply-demand gap when it comes to critical metals that the world is going to face in the next several decades. And today there's a lot of focus on trying to find ways to increase the supply. And the way that supply is typically increased is with new plants, with new processing facilities, higher throughput. But the challenges for that are actually multifaceted. One, it takes 10 to 15 years for most places to basically go through the process of putting in a new plant. You can spend over $1 billion easily on upfront capital to get ready to go, with the ROI being decades long. There's significant challenges with regards to ore grade, meaning you have to process a lot more material in order to meet not just today's production, but the demand in the future. ESG issues are going to make it more difficult with regards to waste and water handling. And as everyone knows, the metal prices are quite cyclic. The challenge is always going to be, are we going to be able to operate in a way where we can be profitable? And the challenges are multifaceted and well known. And what I think we'd like to present to this group today is how Allonnia has developed a new technology that leverages biological chemistry in order to find a way to increase metal supply and capturing value from waste and eliminating impurities. We're going to give you an idea to see how our new technology can be utilized in shorter timeframes with potentially significant increases in metal production. We'll show that our footprint of our technology is actually quite small, much smaller than what you would typically see for a new operating plant. So smaller footprint and smaller capex, which goes along with a faster return on investment. And we're going to show you that this technology can be integrated into current plants, which means you can plug and play this technology into your flow sheet today and start seeing the benefits. But fundamentally, we're turning this concept of waste into value and leveraging a few key components in order to get there. And that is really the fundamental aspect at Allonnia, where we believe that waste is nothing more than a failure of imagination, and it's ripe for opportunities for innovation. So today what we're going to talk about is essentially using microbes to target gangue minerals. Everyone's full aware, again, when it comes to mineral processing, that the whole point is to take the ore out of ground that's low grade and turn it into a sellable concentrate that could be used for smelting and needs to have a particular grade. And the whole mineral processing flow sheet is focused around removing those impurities. And they're ubiquitous. They're found in every single ore body known to man. But the challenges at the end of the day is that using flotation, heap leaching, dense media separations are all standard methodologies that are utilized that all have pluses and minuses associated with them. But they're all focused on well-known and established chemical processes, chemical engineering as well. What we're going to present to you is a microbial-based solution that actually works much differently than what's typically found out in the industry today. That leverages the fact that microbes actually live on these mineral surfaces and they can generate types of extractants that allow us to selectively dissolve away the gangues as opposed to separating them by flotation. So it's essentially a way to improve grade and recovery by using biological solvents, which is a type of biohydrometallurgy. And what's well known again in the industry is that biomining is this diverse field of expertise, understanding, and technologies. Microbes are known to live on surfaces of minerals, on ore bodies. They actually interact with the surface where they physically touch the surface of the ore directly. And they use some of the chemicals that are based in those ore bodies for some of their biological processes to grow and divide. And what Allonnia has presented is this is a type of methodology, again, that's known around heap leaching, where you see microbes sitting in a rather large heap. Allonnia has taken a different spin on this to say we can find a way to use the microbes themselves in order to generate an extractant to be able to improve the quality or improve the grade of a substrate that you would find on site. And so ours is more of an indirect pathway. Consider it something like brewing beer, where you take yeast and you put the yeast in the water with sugar, and as you get fermentation, eventually you make the beer. Our process is very similar to that in concept. And what we've been able to do is leverage this rather diverse array of a biobank that Allonnia has developed over time. These are microbes that have been identified on various sites across the globe, where when we separate them and isolate them, we can understand what types of chemical processes happen inside them, and how can we find a way to leverage those so we can come up with a technology that can be utilized in processing timelines. Microbes are known to degrade ores, but they do it at such a slow pace that it's not really viable for current flow sheet. What we've been able to do is to isolate these microbes, raise them up in the right way via fermentation, and they essentially generate this solvent. So we can physically separate the bugs, if you will, from that solvent and essentially deal with a clean lixiviant. And what we found is that we can adjust the production of this type of material in the lab in order to target certain gangue minerals, and we'll show you some data to support that. And I'm now going to kick it off to my colleague, Karrie Radloff.
Great. Thanks, Dan. So as Dan just kind of spelled out, we're working with nature so that we hit fast forward, so we can do things at mineral processing timelines. So he's kind of laid that all out. Now I get to do the fun part and show you some actual data about what we're doing. So we want to focus with a case study. Can you go to the next one? Okay. So we want to focus first on a case study that involving nickel sulfide con, and the focus is really removing the magnesium from that, because we know that the magnesium bearing minerals can hinder the smelter operation. They have to lower the throughput when you have too much magnesium forming the slag, and it kind of slows things down. So what we want to do is test our biosolvents in a setup that looks familiar to kind of everyone on this call. We have kind of standard agitated leach setups. This allows us to take our entire library of biosolvents that we've done and do targeted initial screening. Once we have kind of these initial results on what biosolvents are working better or not, we can then tune the composition of our biosolvents and test them over again. And all in this setup, we're able to also work towards optimizing the different leaching conditions, things like time of extraction, temperature, and the solids loading. So you go on the next. So this is our work with our initial screening with the nickel sulfide concentrate. So most of the figures I'm going to show you today are kind of set up the same way, where we're looking at the amount of material that was dissolved out of the solid. This one happens to be XRF data, but a lot of it is from our OES. And these are measurements that we're able to do in-house, which allows us to kind of rapidly assess our biosolvent library. So when we do these agitated leaches, we want to look at kind of a controlled known extractant. So in this case, we're using sulfuric acid, and we've got two different biosolvents. Now, what we can see pretty quickly is the sulfuric acid did a good job of dissolving out a lot of the magnesium and a little bit of the iron, but it also solubilized a lot of the nickel. And that, is not what we want. The problem with sulfuric acid is it's not a selective solubilizing, it's, kind of targeting all of the minerals. And it further has the kind of drawback of it's not recyclable. The sulfuric acid in this situation, or in this type of reaction, is consumed. Our biosolvents, on the other hand, we can see in this initial test work, we're able to selectively solubilize that magnesium. You can see that in the blue bars. They were also solubilizing some of the iron, which was acceptable in this case, and leaving most of the nickel behind. So this gives us an indication of two biosolvents to kind of look at, and we can look at the things that are similar in their compositions and then start to tune their composition and how we did the extractions. Okay. One of the things we learned with these biosolvents, and in particular with this material, is that selectivity was strongly driven by temperature. So as we increase the temperature of the agitated leach, we're getting more magnesium dissolution, a little bit more iron dissolution, but that nickel is staying behind in the solid phase. This, kind of gives us that first indication that, we can come up with process optimizations to also improve the selectivity and extent of the solubilization. We've seen similar results to this with other kind of operational parameters. I won't have a chance to kind of show all that data today, but things, in other mining materials, we see similar kinds of reactions, based on decreasing particle size. So, this kind of, all supports our understanding of how our biosolvents are behaving and interacting with these minerals. Next. So the one thing that we saw with this, and we got that indication with the temperature graph, is that the magnesium selectivity can really be improved over sulfuric acid with the kinetics. So if we look at the sulfuric acid extraction that's on the left, so this is showing the percent dissolved, so kind of the same figures as before, but showing how that reaction progresses over time. We see that, the sulfuric acid is kind of readily dissolving things, and that reaction continues. So increasing time, you're just getting more nickel loss. Our biosolvents, on the other hand, have that nickel loss as a kind of a discrete first step, but then it really plateaus. It stays, particularly as we increase the amount of solids loading, steady over time, while we get increasingly more of the magnesium and iron removed. So this tells us that we can do more with our biosolvent to improve that nickel loss, that initial nickel loss, that's not really inherent to the magnesium and iron solubilization mechanism, and then really can drive the selectivity of the biosolvents. So when we start to do this, we want to do a mass balance, right? So what we're seeing in our reactions and thinking about that 20% loading figure I just showed you is if we started with 1 ton of untreated con that has about 10% by weight magnesium in it, what comes out of our process is a much smaller volume, so just under 800 kilos, but we've upgraded that con so that it's got a 5 weight percent increase in nickel, just a 1% weight increase in iron, and a 3% decrease in magnesium. So that means that you're shipping less material with much higher grade and less of the kind of problematic elements of magnesium. So at the smelter, this allows you to put more material through, so you're not having to limit capacity. We also see that with this, in this concentrate, that we're removing arsenic. About 30% of the arsenic that was present has been solubilized. So that allows you to have more flexibility with different penalty elements, and either to not get the penalties or to have smaller ones. But the other thing with Allonnia is we're always thinking about waste. Where's the waste going, and is there something more we can be doing with that? So at the end of our process, we also have all of that solubilized gangue that's now in solution. And we see this as having potentially value on its own. So for every ton of con that we've treated, we have approximately 40 kilos of either magnesium or iron to work with. Okay. So we think one of the real keys part of the value generation with the biosolvents is in this regeneration step. It allows our biosolvent to be recycled and used over and over again, which is completely different from how conventional extractants and or acids are working. We can also readily separate, in this regeneration step, we can separate out those value minerals and see that as potentially a different value stream, either for things to be used in the plant itself or for things like carbon sequestration. This is also allowing us to minimize our nickel loss. That if that initial loss of nickel isn't controlled, we can still recover that nickel downstream, so it doesn't, it's not lost out of the process. And we really see that the regeneration of our biosolvent is the key for this being a viable process at a mining site, because we have to be aware of the water balance and what is the sustainability of our solution in order for it to be adopted and kind of meet ESG goals. Okay. So, so how can we do that? So there are different ways of thinking about regenerating the biosolvent. What I'm showing here are results that we generated in our lab using IX columns. So this we're showing on the left as the biosolvent is being passed through the IX column. It just passes through. So there's the initial kind of plug flow as it's moving through. We're able to recover our biosolvent at essentially the starting initial concentration of it. And the IX column is able to, remove all of the impurities. It's capturing the nickel, it's capturing the magnesium, as well as the iron. And then we're able to recover those elements in the strip step. So in this case, we're using kind of a strong acid IX column, so we're able to use sulfuric acid to strip those metals out. Okay. But what's really key is to look at that, IX data and say, okay, great. Once you've recycled your biosolvent, you've recovered it at the same concentrations it went in, but does it still work? And that's really key. We have to do multiple cycle testing to show, to really demonstrate that the biosolvents can be regenerated over and over again, and we can continue to have these value streams coming out. So again, we started with our leach setup. Here we did each step of our process where we're doing the leach, we're doing the solid liquid separation, and we're doing IX to regenerate our biosolvent. So the second picture is showing you our leachate once it's been loaded with all that gangue. It's got a nice greenish tint. Then we run it through the IX column and it returns to its yellow color. So what does the data look like? So what we've been able to see is that our regenerated biosolvent is showing no loss in capacity in how much it's removing or the selectivity in that when it's doing that removal. So this is 12-hour leach steps, and we're stripping out the cations using just a standard IX resin, and we see that we have a negligible change in that selectivity of how much magnesium is being removed in each of the 6 cycles, how much iron is being captured with that, and that the nickel loss is constant. So each one of these cycles is the same biosolvent having passed through the IX, treating new concentrate. Okay. So how do we tie this all together? We see that this can be a simple bolt-on process to current operations. So as I've described, we've got kind of these 3 core steps where we're going to leach it. We do the solid liquid separation. That gives you the kind of beneficiated concentrate. And then there are different ways to do the regeneration step. I've shared data from an IX column today, but we see that there's other ways to do this. And that with these 3 steps, we're able, we envision that we'll be able to treat just a side stream of data, or the side stream of material, and have that, significantly contribute to plant operations. Right now, we're kind of wrapping up the data from our batch testing, and we're preparing to validate this with a continuous operation of this flow sheet on our first substrate in the next couple of months. And I'll turn it back over to Dan.
Thanks, Karrie. So as you've seen thus far, we've done a fair amount of work in developing this process, this Allonnia biosolubilization process. And where we see its applicability is essentially is using it as a bolt-on solution to current operations. And here you see a kind of simplified flow sheet of a nickel sulfide concentrate plant. And where we are seeing the value of the technologies that we mentioned earlier is that by treating only a side stream of material, we can effectively remove a significant portion of magnesium, which is known to have all these deleterious issues when it comes to nickel smelting, at the flotation step. We can then take that beneficiated material out of our process, send it back to the rest of the process so that the overall grade of the concentrate going into thickening is of higher grade and much lower magnesium. Once it goes to the concentrated smelter, you should be able to push further production of your nickel through the circuit at the end of the day, because what's known with magnesium is that as the concentration builds, the temperature required in order to smelt goes up and the throughput goes down because of the viscoelastic problems with the slag. So by cutting that magnesium level lower, you should be able to smelt your nickel at a lower temperature, saving on energy, saving on CO2 emissions. And if you're bottlenecked at your smelter, you now be able to push further production because that slag can flow out much easier. And as we see in this flow sheet, not only do we have the benefit impact in this simple biohydrometallurgical leach step to increase the grade going through the process, it also provides us a unique opportunity to generate an aqueous stream of these impurities to do something with, as Karrie was pointing out, be it CO2 sequestration or utilization for any other industrial process that might be viable locally where the processing plant is. So you can make magnesium oxide or potentially magnesium and calcium carbonates as either CO2 sequestration targets or to sell the solids themselves. But the big difference is that yesterday, those gangue materials were either ending up in your slag or they were ending up in your tails. And now they're going into neither, and you can do something with it. And so where we see a lot of the benefits are written on the screen, where you can potentially alter the way the mine site is planning to pull ore out of the ore body, not always trying to focus on the highest grade material, but try to find anything that you can pull out and let Allonnia's biohydrometallurgical process remove those impurities. So all of a sudden that ore that was once uneconomic to process can become economic to process. On top of that, we also envision that there's the potential to improve the way the flotation operation runs. Today, there's always the grade recovery trade-off that you have to deal with. You're going to get one or the other, and you simply balance the two in order to maximize the economic footprint. But instead, if you were able to run your flotation circuit by maximizing recovery and getting higher mass pulls, would you then be able to then subsequently use our process to allow you to make the grade by dissolving those gangue species away? But because your recovery has increased, your overall throughput to the plant has improved. And so what we see is with a single step, essentially, we're able to drive increased value with the generation of higher throughput or lower costs with regards to making your ton of metal, a pathway to lower CO2 emissions on the plant, and to reduce the amount of tails that you generate, all in the same separation step, with, as we envision, a relatively small footprint, because as you noted in Karrie's data, the amount of material we're able to remove is significant, and you don't need to necessarily remove all the magnesium from your nickel stream. But if you're able to remove a portion of it very efficiently, you can control the final targets of what it is you're generating in the concentrate. And where we see that of kind of interest is that while we kind of gave a case study with a particular substrate, we're now looking at other nickel sulfide substrates that we found across the globe. And we're actually getting reasonably similar data. Right? At the end of the day, the mineralogy has some similarities and some differences, but in these instances, we're able to still remove a good amount of iron and remove a good amount of the magnesium. And key point in here is that almost all the iron we're removing is basically iron oxide, and the iron sulfide is staying behind. Important reason is that that iron sulfide is used as a fuel when you get to the pyrometallurgical step, and it's not beneficial to remove it. What we're seeing is that our biological solvents are really just consuming the oxides, leaving the sulfides behind. Additionally, we see that from the same substrate, we can tune the composition of these solvents, as we mentioned earlier, by changing the way we raise the bugs. And by doing that, you can essentially generate a new type of extractant that could be more specific for a particular gangue mineralogy versus others. And here you see a piece of data that's similar to what Karrie showed with Biosolvent 2, where we're looking at trying to remove magnesium. And then another one that we've developed where we're now starting to look at silica and removing certain types of silicates that are present in these concentrates and getting them into solution. Now I'll turn it back over to Karrie to finish off the talk.
Yeah, so I just want to, share with you a little bit more data of kind of other materials that we've looked at, that, that these biosolvents are not just working with nickel sulfide concentrates, but we've actually looked at kind of a wide range of materials. So I have one example from each of these that we can kind of go through now. So when we've looked at ore materials, so this is actually showing results from several different ore bodies that were located kind of in a geographically similar spot. Here we're really targeting the kaolinite removal. We want to get out silica and aluminum. And what we see is that with just 2 hours of treatment with our biosolvent, so that's one of the other things that's really interesting. Each of the biosolvents kind of behaves in a different way. So this one was a much faster reaction. It was at a lower temperature, and we were able to remove about 30% of the silica and just over 20% of the alumina that was present in this ore, and that allowed for an increase in ore grade. Okay. We've also looked at other concentrates. So this is an example of a copper con, where we were looking at screening it against our kind of library of biosolvents. Again, I'm showing 2 examples here. Here we're really focused on removing silicates, specifically kind of magnesium-bearing silicates. So we're trying to get increased amounts of the magnesium in the silica out, and that's the kind of the yellow and blue bars. And if we look at our controls, kind of typical ways you could do this with an acid leach or a base leach, you could, particularly with sulfuric acid, you can remove a lot of the magnesium, but you're also going to remove a lot of the copper with it. And, kind of the sulfuric acid control, you've solubilized almost 20% of the copper in the con, which is obviously not good. With the biosolvents, with particularly biosolvent 3, had almost the same amount of solubilization of magnesium, and it actually had greater solubilization of the silica and almost no loss in the copper. So we see both biosolvent 3 and 4 as having great potential. So now we're starting to look at their compositions and tweak them. We can also potentially blend our biosolvents to really target the specific minerals we want to dissolve. And lastly, I want to just touch on some work we've done with tailings. As Dan mentioned, a lot of places are starting to think about carbon sequestration, and tailings is particularly an area where there's been a lot of talk about the carbon capture potential of tailings, but there's really no viable process. So how can you leach out the magnesium and calcium to make them available for carbon sequestration at anything remotely close to a reasonable time scale? So what the data we're showing here is with 3 different biosolvents, and you can see how we can kind of tune which biosolvent we're using based on what we want to solubilize. So biosolvent 1 did a great job of solubilizing the magnesium while leaving more of the calcium behind. Biosolvent 3 kind of had the opposite effect of solubilizing more of the calcium, while biosolvent 2 was able to pretty effectively target both of those, and is, again, performing at a level that's kind of similar to sulfuric acid, except it has all the advantages that we just talked about in the case study, and that we're able to regenerate this, get the value out of these solutions, and reuse our biosolvents again and again. Yeah, so we're really excited about our process, and we've kind of honed in on how to screen our library of biosolvents, and we're learning about which materials kind of behave, how they react to different biosolvents. But of course, our learnings are limited by how many different substrates we've been able to test. So we would, love to talk to you more about our quick screen process. How do we get your substrates into our lab to kind of test against our library, see how they perform, kind of do some initial work looking at these experimental conditions, and then can share this data back to kind of show the potential of our biosolvents for kind of removing all sorts of problematic and penalty elements. So thanks. We're happy to answer questions or.
Great. Thanks, Dan. Thanks, Karrie. For the folks that are online, if you have any questions, now is the time to enter them into the Q&A box. But maybe I'll kick things off. So just you've been doing a lot of these experiments, you're testing different substrates. What's next for Allonnia?
My primary focus is getting our continuous operation running. That we want to show this, that it technically works and that economically it works. So that is really the target, is to put our, we have our 3 steps, kind of integrated at a batch scale, and to get that into a continuous operation.
And we're working with a couple of metallurgical labs well known in the industry that can handle these types of materials, and they can run these types of processes with a goal of operating somewhere in a window of about 5 to 10 days at roughly 5 to 10 kgs per hour of concentrate, so that we can, as Karrie pointed out, validate both the technical performance over time as well as the economics. And we believe that with that data and some of our current partners, it'll allow us to hopefully go to the next stage, which is to then talk about using a mobile pilot unit, where our goal would be to bring in 1 or 2 shipping containers of size on site to actually operate with the plant, taking a side stream off the current operations and running it continuously with the local engineers.
Great. So we do have a couple questions. The first one is there any copper recovery from tailings?
In the material that I just shared, there was only, I would say, kind of trace amounts of kind of value elements that were in there, but some of them were solubilized. I think it would be highly tailing specific, based on what minerals were there. But we'd be happy to try.
Yeah, fair enough. And then another one here was, do your biosolvents have the same pH as sulfuric acid?
No, they are running at a higher pH.
Okay. And then another one here, by the way, lots of folks think this is very interesting, about the fungi or the bacteria that you use to generate the solvent. If you're allowed to say, what carbon source do you use to grow them? They go on to say, I know the use of heterotrophic organisms in mining is sometimes limited by the cost of organic carbon substrates.
Yes, so right now, we're doing things at the lab scale. So we're just using kind of standard, lab grade carbon sources. We recognize that to bring this to commercial scale, that we'll need to be working with waste carbon sources that we're not going to feed our microbes glucose to make this. That won't allow for an economic product. We have a dedicated fermentation team and synthetic biologists who actually, they have their PhDs in how you kind of either engineer, mostly how you engineer or kind of do adaptive evolution so that these microbes will produce the same metabolites using waste carbon sources. So that's like a separate area of development that we're working on.
That's a whole other opportunity to turn waste into some kind of product as well. So very much in keeping with the ethos behind Allonnia.
Yeah, and it'll depend a little bit on whether, the plants that these will operate on. right? That,
Yeah.
Looking at the waste carbon sources that are more locally available will be key.
Bespoke bacterial biosolvents.
That's our plan.
Fantastic. Anything, it might be good for the folks at home too, maybe just to provide a little bit more background on Allonnia itself, the company, how it got started, what you guys were all about. That might also provide some good context for the folks here.
Sure. So Allonnia has been around for about 4 years. We were spun out of Ginkgo Bioworks, another startup that came out of MIT in the Boston area. Ginkgo Bioworks very much focused on synthetic biology and basically building platform technologies and trying to understand how they can kind of teeter around more with microbiomes and synthetic biology in order to develop capabilities for developing new technology. What Ginkgo Bioworks didn't want to do is get focused into product development in certain areas. And so they had a strategy of essentially spinning out companies from under their umbrella to tackle those challenges. And one of Allonnia's the reason Allonnia was spun out is essentially to look at environmental challenges and how do you use microbiology and synthetic biology in order to solve some of those key issues that are found across the globe. Today, Allonnia is basically in two separate groups that we have within our company. One is really focused on waste remediation, particularly with regards to PFAS removal. We have a technology called SAF, surface active foam fractionation, that can really selectively remove PFAS from water, where you can essentially take 1 million gallons of water that's contaminated and you can take all that PFAS and put it into a single gallon of water. We're selling those units at various parts across North America, and they're utilized in lots of different applications. The other side of Allonnia is really focused on mining and trying to understand how do we leverage kind of that core technology that came through Ginkgo and is now being improved by Allonnia scientists in order to develop a product to sell or a process to sell or both. And that's really where the focus of the biosolvent team within Allonnia has been working on the last year, is trying to understand the chemistry around the biological solvent, how it's made, how it's utilized, trying to then use chemical engineering tools in order to build a process, and then working closely with the mine sites in order to find a way to remove those deleterious minerals so that we eventually can bring to market a technology that comprises both an extractant as well as a process for the industry.
Fantastic. Thanks, Dan. We did have one last question come in as you were chatting here. It would be interesting to treat complex sulfides with flotation producing multiple concentrates, with cross contaminants with penalties. Have you tried treating those concentrates?
Some, I guess, our kind of library of the concentrates that we've worked on is more limited. So we targeted some penalty element removal, looking at things like arsenic, of course, cadmium, and chromium, I think, are the three that we've really focused on. But we're actually kind of gearing up to kind of expand the list of penalty elements that we're looking for. We certainly see that there's a lot of value in, the ability to target, kind of more specific mineral groups where we think that these penalties elements are present, and we would welcome a chance to kind of to give it a try on a different substrate.
Great. There's also, I've been ignoring the Q&A section, but there's a lot here in the Q&A. I'm not sure if you guys are able to see it as well yourselves.
Not really, no.
Okay, there's one on sort of throughput volumes are these biosolvents capable of, but I think at this point it's still kind of lab scale, correct?
Yeah, I mean, we're moving towards demonstration operation, and the goal there is about 10 kgs a day of flow. So we're not talking about a significantly large unit. I mean, so our goal now is to really validate that the extractants are recyclable, as Karrie has pointed out. The lab data where we do this in a discontinuous fashion suggests the answer is yes. Our next step is to prove that it works continuously, and then start building up scale from there.
Yeah, but in terms of like scaling up biosolvents, that's an already solved problem in that, you know, fermentation science has advanced. We can take our strains and bring them to, larger fermentation units, and they will behave the same. We will be able to generate the kind of volume required for the larger units. The constraint won't be making the biosolvents.
Couple more here. Can you provide some more detail for what the MgSI, or the magnesium sulfur stream, looks like when it's generated by your process?
Sorry.
So that's asking about magnesium silicates?
Yes, sorry, so SI, yes.
Yeah, right.
So what we're separating out from the concentrate is fully dissolved. So it's, that these elements are present as dissolved species in our biosolvent, which is how we're able to regenerate them, both to recover the biosolvent and then to separate out those different elements. What that stream looks like will depend on the technique that we're using to do the regeneration. And at this point, we've tested out a couple of different conventional technologies, including IX, but I think there's more work to do on that front. And it depends kind of what we want to have those purified Gangue streams look like, could also inform how we want to do the regeneration.
We'll do one more here just to respect everyone's time. I think this is a question I also had, but is the solvent potentially applicable to in situ leaching?
Yeah, we have not looked at that part yet. At a high level, of course, right? It can be used in heaps in the same way. I think from an economic viability, we haven't addressed that question yet, or we haven't looked at how to do that.
Great. Well, again, thank you everyone for your time today and for joining. There are a bunch of questions here, but there's a couple more, but I know the gentleman that's asking them, so I can get them in touch with you folks. We will be following up with a just following up on this. So if you want to get in touch with the folks at Allonnia, their contact information is right there for you, so you can follow up directly or through the follow-up that we'll be putting out. The recording as well will be available. So thank you again very much for participating, everyone. And yeah, thank you, Allonnia, for taking the time to present today on this very interesting technology that hopefully is able to scale up and solve a lot of these problems we have with waste streams. That would be fantastic.